Hello, everyone, and welcome to this session organized by Jnana Prabodhini Foundation's Analytics Group. Today, we'll be talking about data for social good, an introduction to computational social science. Let us begin with a few examples. One example is about how mobile phone data can predict unemployment. This was a study done in Europe, in two undisclosed European countries to be specific, where a group of researchers analyzed a lot of mobile phone data. This was all anonymous data, and this data represented about 20% of that entire country's population. Based on analyzing the mobile phone signals and mobility data, these researchers were able to infer unemployment at a micro level and also predict employment at the country level. Let's take a look at another example. In this example, we saw Twitter data being used to predict earthquakes. This was done in Japan, where they analyzed tens and thousands of tweets, tens and thousands of real-time tweets about Twitter users who were just posting their opinions, their beliefs, their observations about earthquakes. They found that this model can not only detect earthquakes in real time with a high accuracy and also a high speed. Finally, let's take a look at another example. Some of you might be more familiar with this example. This is about how mobility data obtained from mobile phones and GPS can be used to track and predict disease spread. Most obviously, this was done in the context of COVID-19 pandemic, where multiple governments across the world were using contact tracing digital mobility data to inform their real-time understanding of the pandemic, as well as take real-time decisions of pandemic mitigation measures. So what is common from all of these examples? They are admittedly pretty diverse. I'll give you a minute to think about it. What do you think all of these examples have in common? Well, one of the things that they have in common is that they actually had an impact on the real world. They improved traditional systems. For example, unemployment is traditionally measured by using surveys. In the United States, the US Bureau of Labor Statistics has been measuring unemployment data from the 1940s. However, such metrics of unemployment are often tedious, time-consuming. They require a lot of human resources and labor, and many times they do not give real-time updates. Such unemployment estimates are often available only months after the data was actually collected. In this context, the study that we saw was able to not only detect unemployment on a real-time basis, but also predict future employment with high accuracy. This is how this study and this system was able to improve upon one traditional way of measuring unemployment. Another way of how these examples improve traditional systems was in our earthquake example. As I mentioned, this example or this study was done in the context of Japan, where there are a lot of earthquakes happening. And traditional government agencies, such as the Japan Meteorological Agency, has its own set of tools and methods and models to detect earthquakes and other natural disasters, such as tsunamis in real time. However, not only was this Twitter-based system able to detect earthquakes with the same accuracy as Japan's meteorological agency, it was also able to do it faster and send real-time updates and warning messages to humans. Finally, traditional contact tracing about diseases, infectious diseases, is done by house-to-house surveys, where you track down infected populations, you track down their mobility data, you track down their social network, you track down what their day-to-day habits have been. As you can imagine, such methods are very costly. They require a lot of human resources. And during the context of a pandemic, they also endanger the lives and the health of those involved, the human resources involved in these such tracking metrics. In such contexts, digital contact tracing endeavors can greatly reduce the cost of contact tracing initiatives, increase the coverage of contact tracing initiatives, and often, not always, increase the accuracy of such contact tracing initiatives. Thus, you can see that all of these examples that we talked about improved traditional data collection systems. And that is one commonality that they share. Can you all think of some other commonality that these examples shared? Well, one of the other commonalities that these examples shared was that their use of digital big data. They all used large-scale digital data sets that were only possible due to technological innovations that have been invented in the past few decades. It is worth mentioning that we are living through what is called a computational revolution. Humans create and consume zettabytes of data. And this is really a lot of data, and it is increasing at an exponential rate. By 2025, we are estimated to create and consume about twice as much as data that we are using today. And this amount of data it's about 100 times as much as what we were doing just 10 years ago. So the data that we create and consume is increasing at an exponential rate. In the context of India, we can see that internet usage and digital mobile penetration has also been increasing in the past few years. By 2025, we will have a large chunk of the Indian population online. All of these social changes and these technological upheavals present with them many opportunities and also challenges. They allow us to get access to a wide range of new types of data. And as we have discussed in previous sessions, data can mean many things, including quantities, informations, measurements, observations, numbers, facts, and graphs. We have also previously talked about how such data can span many domains. Data can be about geographical systems, it can be about culture, it can be scientific data, financial, statistical, meteorological, natural, and related to transportation systems. And we have talked about how there is a need for efficient and robust data analysis pipelines that can transform this raw data into refined insights that can actually impact the world. In this context, a new field has been emerging that leverages some of these technological upheavals and social changes that we are seeing. This field is called computational social science. Now, computational social science, just like that classical adage or tale of the blind man and the elephant, has many definitions and many understandings. Different practitioners and theorists define and use computational social science in many different ways in their day-to-day lives. For our sake, we will focus on a simple working definition of computational social science, where it has two important characteristics. The first characteristic of computational social science is that it involves large repositories of digital data about human behavior and societies. The second is that it leverages computational methods needed to construct and analyze such data. Computational social science data is wide-ranging. It leverages a range of different methods from the computational sciences, such as agent-based modeling, social network analysis, geographical information systems, machine learning, and digital content analysis, such as sentiment analysis, that allows it to answer some of the questions and make impacts in some of the fields that have traditionally fallen under the umbrella of what are called the social sciences, such as anthropology, geography, political science, economics, history, psychology, sociology, and so on. Computational social science represents the ideal intersection and cross-pollination between these two fields. And therefore, what skills does a computational social scientist need on a daily basis? What does a practitioner, what do you need to be a successful social scientist, both in industry, in academia, in the nonprofit sector, in many different sectors in which a computational social scientist operates? Obviously, you need core computational competencies. You need to be able to do programming, and typically within computational social science, R and Python are the open source languages that are used. You need knowledge about inferential methods, that is, methods that allow you to rigorously quantify and justify the claims that you are making. This can be traditional hypothesis testing or statistical modeling. You would also need some kind of specialization in some domain-specific skill. Now, that skill could be natural language processing, it could be survey methodology and experimentation, it could be geospatial visualization, and many, many more. There are many domain-specific skills that are applicable in this context, and having knowledge of at least one specific skill will make you a successful computational social scientist. Importantly, though, you would also need, beyond this domain-specific skill, a familiarity and working knowledge of cutting-edge digital technologies. For example, you would need to know about some of the recent machine learning and artificial intelligence methods, such as large language models. You might need to be aware that ChatGPT-4 is the most recent model, not ChatGPT-3. And by the time you see this video, ChatGPT-4 might be grossly outdated. So you need to be able to keep track of everything that is going on in a real-time basis. The computational revolution is a revolution, and therefore it is fast changing. Being aware of what's going on allows you to make a bigger impact in this field. Importantly, it allows you, as a computational social scientist, having these skills to leverage the promise of big data. Big data has a lot of allure. It is very glamorous, and it has, as some authors argue, the potential to completely end science as we know it or transform science as we know it today. Why do you need theory and models and causal explanations if you have a lot of data available? Just use big data and come up with all of your answers. You may not necessarily need rigorous theories or explanations of what is going on in the world. Is a perspective that some often argue, and you may see, especially in many of the fast-paced domains that use computational tools, computational social science tools, such as big tech, social media industries, and the financial sector. And this is not unwarranted, because the computational revolution did affect many fields. Many of you, or some of you, may be familiar with the image that you see in front of you. Does anyone know what this image is? Yes, this image is actually the entire human genome. And you can kind of tell the numbers that we have are the individual chromosomes, and you can see the X and Y chromosomes right up there at the top. It's the entire human genome of a person printed out in books. And if you decided to read these books, you would take about 100 years to read all of these. Mind you, this is the amount of information present in every cell of your body, and your body has trillions of such cells. And the computational revolution, beyond affecting fields like social sciences, which is the focus of our session today, has also transformed many other fields, most obviously the life sciences and biology. Today, we don't need a multi-billion-dollar human genome project to painstakingly isolate and describe the genome of one human using such books. We do it rapidly on a day-to-day basis, and that is what we did in the COVID-19 pandemic. That is how we were able to even come up with a vaccine for the coronavirus, because the moment these diseases were detected, detected, life scientists such as genomicists sequence the genome of the coronavirus. Thus, data and the computational revolution definitely has a lot of potential. However, it specifically has a potential in the context of making fields more rigorous or quote unquote hard. And I'll just throw out a funny comic out there. This might reflect some of the intuitions that we have of some of the scientific fields out there, of how if you do physics very rigorously, it eventually transforms to mathematics. If you do chemistry more rigorously, it eventually transforms into physics. If you do biology more rigorously, it just transforms into chemistry, and so on. And maybe an intuition you might have about computation, about the social sciences, is that with more data, they will eventually become more and more rigorous and more hard or quantitative sciences. However, as we have discussed in previous sessions, that even though quantitative data is very useful to make decisions, to make predictions, quantitative data is not everything that is there in the world. Quantitative data also has its own limitations, as very succinctly conveyed in this XKCD comic. And therefore, in addition to quantitative data, qualitative data is also equally, if not more important. And one should emphasize that getting data for computational social science is challenging. Unlike simply extracting data from human digital motions or digital traces, such as social media data or human mobility data, these data are often controlled by companies such as big tech companies. And these data are often behind silos. They're not accessible to the general public. And to do effective computational social science, not just for the profit of a company, but to actually have impact on social good, you need to get access to data and make it openly available to a range of stakeholders, including the government, representatives of civil society, citizens, researchers, and so on. And therefore, we propose a modified definition of computational science, social science. Of course, computational social science involves large repositories of digital data about human behavior and societies. And of course, it involves the computational methods needed to construct and analyze these data. But computational social science is not limited to these. It also involves a convergence of different fields with different ways of thinking, and it involves new ways of doing science. Let's take an example. Let's continue an example which we introduced at the beginning of this session of how mobility data using our digital technologies such as phones and GPS can be used to predict disease spread. The reason why mobility data can be used to predict disease spread is because disease transmission is also a social scientific process. There are multiple mechanisms of both local transmission that you see at the left of your screen and large-scale global transmission that includes seasonal and long-distance transmission that you see at the right side of the screen. Local transmission accounts for the places that people engage with and enter and go to in their daily lives, such as their homes, religious and social places, water locations, marketplaces, their farms, health centers, their workplaces, and the homes of their social acquaintances, such as their friends, families. More long-term mechanisms of disease transmission involve international travel, holiday travel, labor migration, and seasonal agriculture. And therefore, a more robust model of infectious disease spread would have to incorporate all of these aspects to come up with more impactful insights. Just to give you one example of how this can be incorporated, in sub-Saharan Africa, there is a region called the Sahel, and the Sahel is characterized by seasonal rains. It includes many nomadic pastoralists, that is, populations whose primary occupation involves rearing sheep, goats, and other cattle, as well as small-scale farming. Many of these populations travel across the Sahara Desert in the Sahel region in different time points of the year. They do this because they are following the rains, they're following the pastures in the Sahel. And therefore, these migrations of these nomadic populations can be accounted for the dry and the rainy seasons. Oftentimes, these migrations are blind to the restrictions imposed by national boundaries, by social boundaries, and therefore an accurate model of disease spread would not just say take a look at how a population, a largely local population in, say, New York or Pune functions, but also how nomadic populations function. That is the insight promise of what social science, computational social science occurs, not only using big data to understand human behaviors, but also tapping into the insights from traditional social sciences, from anthropology, from human behavior to transform the uses of digital big data. This is especially important because social scientific systems are complex systems. There are rarely what are called kind problems that are very neatly defined problems. Kind problems are problems such as chess or golf, where the rules are often very clear and the outcomes are very predictable. They would be what the physicist often jokes as the spherical cow, or more formally, what we call free body diagrams in physics and engineering, where we abstract away from all of the complicated extraneous factors and only focus on the relevant forces affecting a system. But unlike natural scientific and physical scientific phenomenon, social scientific phenomenon rarely have such kind free body characteristics. They are complex, susceptible to multiple feedback loops and interactions, and they involve nonlinear dynamics. They'll involve insights from many different domains, such as network theory, insights from collective behavior, from game theory, from systems theory, from evolution and adaptation, and from pattern formation. And having a knowledge of how all of these intricate feedback loops and processes affect the evolution of a social scientific system over time is crucial to being a good social scientist. And therefore, a good computational social scientist, in addition to their core computational competencies, also needs some core social scientific competencies. A good computational social scientist would have to work with large, messy, complex systems and data. They would need an interdisciplinary mindset, the ability to go beyond silos, the ability to appreciate that the world around us is not neatly divided into science, commerce, and arts, into engineering or medicine, into STEM or humanities, and that most problems that we deal in the world require actually a lot of most of these issues. You cannot just be a master of all and a master of one and a jack of all. You need to be a master of at least one and a jack of many things to be a good computational social scientist. Therefore, you need domain-specific social scientific skills from, say, organizational and behavioral science. You might be aware of the standards about community trust, safety, and engagement. You might have domain-specific knowledge about demographic, population, and geographical studies. However, you would also need real-world knowledge about data sharing, privacy, and ethics. We do not have time to go into all of the issues that arise with big data and social media companies, but many of you may have been following these in the news of the pitfalls and the problems that can arise with large, powerful companies or governments or individuals or institutions having access to closed data sets that can allow them to not only get insights about human behaviors, but actively impact and change human behaviors. Finally, a good computational social scientist needs to be able to communicate with a wide range of stakeholders, including think tanks, media, nonprofits, industry, academia, and government sectors. A good computational scientist would also have to write their findings in rigorous academic language and publish it in a peer-reviewed journal that might take 2 years. At the same time, they might need to work with nonprofits and governments to ensure that their findings don't sit in a drawer and can be actually used to impact real-world rapid changes. So a good computational social scientist would have to pay attention to all of these facets. And that is all that we had for today in our session about data science for social good and introduction to computational social science. Thank you for attending this session, and we hope to see you next time with a new topic about data analysis and social science. Thank you.